Hi, my name is Matt, and this is my Lab 2 slide deck. So for a quick introduction, everything is around the same as last time. The purpose was to observe the interaction between two strips of charge tape, but this time we modeled it as a line charge model instead of a point charge model. So some principles and nomenclature, same as before. Mainly the most used Physics 2 concept here was the electrostatic force equation, which is listed on the right. And then another important mechanical property we have is the result of gravity near sea level, the resultant force, and that is also listed to the right. So some assumptions and setup. One really big assumption that we had was that these two tapes were the exact same dimension, and therefore they would carry the exact same charge. That's really important in our computational model because that is a big assumption that we make. Air resistance can be ignored here because both these tapes are in equilibrium, meaning that the net force acting upon them is zero, as well as the fact that neither of these tapes are in motion, meaning that there is no air resistance. This time the tapes were not point charges, so we modeled them as a line of charges. The tapes were held perfectly parallel to one another. That is also a very important assumption that we made in this line charge model, even more important than the point charge model, because now this time we have to have two lines that are actually parallel. And the last assumption that we made was that the hands that we used to hold the tape did not interfere with the tape in any sort of way. And for example, they didn't strip any charge from the tape. So some initial observations before we get into things. The tape seemed to be positively charged as it repelled itself and was attracted to a negatively charged plastic pen. And then from eyeball measurement and with a ruler, 2 centimeters of separation was needed to float the suspended tape. So some quick calculations, the same as last time. What I really want to highlight here was that last time we found that the charge on the tape was around 9.3 times 10 to the negative 9 coulombs. So simulation and code. On the left, you'll see the initialization code, and on the right, you'll actually see the loop that was used to calculate the net force. You'll see that the Q, which is the charge estimated, is different than from the previous slide. This was attained through guess and check. So basically one value was entered and then it was changed based off the resulting result and seeing how close it was. The resulting new answer is around 10 times larger in magnitude. The function for calculating electric field is pretty straightforward, just using the electrostatic force equation and then stripping one Q off because, we assume that both tapes have the same amount of charge. And then on the right, we just have a standard loop for calculating the electric field of each particle on the combined electric field of each particle at each particle from all the other particles. So this is the result. As you can see, the magnitude of the electric force and the magnitude of the gravitational force are around the same. And you can also observe particles in the middle have only positive y-axis basically for the electric field, and whereas the ones on the side have some x-axis to them. That's because of the fact that there are no more particles on the other side to cancel out any lateral movement or any lateral electric field. So some possible sources of error. One big one was that the measurement tape was actually a different distance than what was observed, so measurement error. The tape didn't lose any charge to our hands. Again, that would change the amount of charge, and then the tape was held parallel. This is especially important because in this simulation, the two lines must be parallel in order for this calculation to be correct. So some what-if questions. If you had modeled each of your tapes as a single point charge like in the previous lab, compare the estimated value of the charge you get when you use experimental data to produce a point charge to your line charge. As we saw, the point charge model severely underestimated the charge of the charge tapes, whereas this time the answer was off by a magnitude of 10 around. So why do these estimates differ? Which value is more likely to be the real value and why? The computational model is more likely to be more accurate because it makes less assumptions than the point charge model, namely that the tapes are not actually point charges in real life, and the computational line model more accurately reflects that. So as a conclusion, the computational line model is more likely to be more accurate, and it gives us a different conclusion than the point charge model, which in my opinion is more likely to be correct. Thank you.